name is Dimos Dimarogonas, and I have the honor and great pleasure to introduce Professor Luca Zaccarian, Directeur de Recherche at CNRS in LAAS Toulouse, and also professor at the University of Trento. Luca has a great number and amount, both equality and quantity of contributions in nonlinear and hybrid systems with applications in mechanical systems. And I think this touches upon the topic of today's semi-plenary. And he has, of course, as many of you know, a great contribution to the community with being a member of the Board of Governance of IEEE-CSS, member of EUCA, of IFAC in various editorial roles in prestigious journals, lately also senior editor at Automatica, as I very well know, also. A number of awards, such as the Hugo Schuck Award in 2001. And more importantly, I have had the pleasure to visit both Toulouse and Trento in the past. And we had a number of very interesting discussions about life and about research. And we're going to get some flavor of the latter in today's semi-plenary. So please join me in welcoming Luca.
Thank you very much, Dimos. Thank you for the kind introduction. And thanks everybody for attending. It is a real pleasure for me to speak at ECC, and I would like to thank the organizers for inviting me. Evcharisto. I'm trying to learn Greek, but it's tough. It's a hard job. Okay, so assuming I can make my pointer work correctly, today I'm going to discuss a few examples, a few applications that I've been addressing where the closed loop that you get enjoys a specific structure comprising linear time-invariant flow intertwined by jumps, by resets, which are tailored for the application. So there is a specific underlying pattern that I would like to show you and I would like to discuss as an emergent thing that is worth some attention. Now, beginning, I would like sort of to convey a philosophical structure of control. So we are used to think about classical control system as a continuous time plant governed by differential equations. And then the controller in a classical design is another differential equation with a state xc, which exerts some action on the plant. So this exerting that I'm introducing really gives you the idea of pushing the plant in a certain direction. And in fact, the whole feedback structure is based on the action of this input u, which moves the trajectory continuously. It is sometimes natural for the plant to be, in fact, continuous because of the structure of it, but very often it's not convenient to have a continuous evolution for the controller state. Why not resetting the controller state to something more convenient at some moment? And that's where I want to introduce this other paradigm where we augment the exert with two actions that I call the detect and the reset. So the reset is roughly, it's intuitive. It's essentially, you think about this evolution, this closed loop, as a bunch of possible solutions that you could get. And then the reset can assign, like in an orchestration, a new evolution that you want to obtain. And the thing is that the detect will be the mechanism upon which you do the orchestration. Okay, so these new ingredients, detect and reset, will augment our closed loop. And in fact, they make sense only if the controller is a dynamic controller. So if you have a state that you want to reset, and indeed, you can immediately draw some immediate advantages from this. Like, for example, the controller state could include the logical states, and then the reset allows you to orchestrate among all the different modes of this sort of switching system. Or it could include timers, as I'm going to show next. And timers could be used also for the detect, right? But in general, throughout today's talk, I would like to emphasize how LTI flow is key to proving properties of this closed loop. That's something that is a trick that is pervasive and that I've used a lot. Okay, so let me start with the first example, which is fairly similar to the initial circuit shown by the plenary speaker this morning, and it's self-oscillating control of resonant converters. So resonant converters correspond to transforming DC input, constant voltage, into an oscillating voltage at the output, or current at the output. The way to do that is to build a resonant tank comprising LC components, which has some resonant frequency of its own, and then switching the input sigma among a family of values that can be -1, 0, or 1. So that's all you can do, right? And then, because of the resonance, what you find out is that even the amplitude of the output can be larger than the amplitude of the input. Now, this type of circuit is very relevant in a number of power systems applications, like battery charges, power supplies. And I learned about it when I was visiting the University of Tarragona a few years back. And then the work that I'm going to tell you about is with our former PhD student Nicola, my colleague Isabel, and our colleagues Luis and Carlos from Tarragona. So let me give you a little bit of context, okay? So we have, for second-order resonant tanks, you can see the resonant tank is this parallel interconnection of L and C, or this series interconnection here. So one of them is called parallel, and the other one is called series resonant converter. R is the load, so the load can be represented by a resistor. And what is interesting about these two schemes is that if you define the state as a normalized voltage and the normalized current on the two capacitors, and so these are the selections, you get a single set of equations that describes both configurations. In fact, the dynamics, the underlying dynamics is the same. The beta is different, and it's the inverse of the time constant. And the omega is the resonant frequency of the resonant tank. Now, what can we do with this equation? So let me put it at the top. If we think of sigma, as I mentioned, as a state of the controller, then we can perform a change of variables, and this dynamics transforms into an LTI flow. Now, this is very convenient because we will see in the z-plane that the action that I call the exert here is essentially a revolving trajectory corresponding to a damped oscillator. Okay? And it turns out power systems people, power electronic people, they know very well that for this guy to work, the resonant tank must be resonant. That means that this oscillator must be underdamped. Now, once we transform the dynamics, the flow dynamics like this in these coordinates, this is immediate as an assumption. And for any value of beta, which is small enough so that these eigenvalues are complex conjugate, the scheme will work. Okay, so the exert action in this system is essentially just an open loop behavior of the resonant tank. Now, what happens with the reset and with the detect? So to explain it, let me cast the dynamics as a hybrid dynamical system where the previous equation is this one here, right? Remember that sigma is the state of the controller, so its derivative is 0. And then we look at what happens if we switch the input sigma. And let's look at the simpler case where sigma can be either -1 or 1. Then when you switch, you just toggle. So you take this h to be just minus sigma. Of course, the switch also affects the Z1. Remember that Z1 contained sigma in its definition. So that's what we do. And for the detect, we need to choose the set D where, you know, this switching is imposed. And so the set D, what we're going to do, we're going to select it as a line in this z-plane. So we will exploit the z-plane description, knowing that if we take a line passing through the origin, the trajectory will keep crossing it, and that will be the trigger, right? That will be the detect. So let me be more specific. Let's talk about the reset first. And I'm going to show you two practically relevant techniques. The first one is called frequency modulation, and it's the one that I started talking about, where sigma is just -1 and 1. So when you switch, what you see is a pattern like this. So what you do is you toggle sigma at resets, Z1 changes, and this is the pattern you generate. For the second case, which is called, this is called frequency modulation because it turns out you adjust frequency and amplitude with this type of strategy. And the other one is what is called amplitude modulation, where you have 3 levels for the input now. And there is a specific pattern that you should follow. And the way you encode it in this reset map is by adding a new state D, which stands for direction. And this logic, trust me, generates exactly this type of behavior. Okay? So that's the reset. Now, the detect is the most difficult part. It's the more sophisticated, let's say. And let me discuss it separately for the 2 cases. So the detect for frequency modulation, as I mentioned before, is this line, which of course, is also dependent on sigma so that you don't get weird uncertainties in the switch. And because of this, when you look at the motion that stems from this behavior, you see essentially an LTI motion in this part, and then a jump that happens here that corresponds to the switch. So in the LTI motion, energy is dissipated, and then across the jump, energy is injected. And what you can get is that you obtain a single asymptotically stable limit cycle for any value of this angle theta. So if you adjust theta, you will get a different behavior, and this parameterizes the output frequency and amplitude. So it's like your reference input to the actuator. And if you look at the other case, it's a bit more complicated. So if you have these 3-level inputs, then the orchestration is a bit more sophisticated. The angle is this phi, which is the same as in the other side. All of these branches are, in fact, LTI flow. And then you get this weird-shaped hybrid limit cycle that you can generate. Okay? Of course, the input then will look like this. Now, it's a bit difficult to digest. So let's remind ourselves that this is the z coordinate. If we look at this in the x coordinates, which are just the voltage and current, they're of course continuous because of physical reasons, but this is the type of behavior that you will see on the scope. Okay? So with this plane, however, these are not LTI flows, so there's little we can conclude, at least with the tools I know how to handle. But if we use the z-plane, then we can prove that for any value of theta or for any value of phi for the 2 schemes, there's a single hybrid limit cycle which is almost globally asymptotically stable. Almost globally meaning that at the origin there are issues because of, say, multiplicity of solutions and other weird xenomathematical things coming up. And anyway, I think you could improve well, whatever. So this is the Lyapunov function induced by it. You see the hybrid limit cycle here. And here it's represented in the x-plane because the other one, the z-plane representation is a bit messy. So I think this is more intelligible. OK, so before closing this part, I just wanted to show you experiments. So Nicola was brave enough to be able to implement this. And you see here a trajectory for one of the frequency modulation scenarios. And of course, the experiments confirm the theory. So the left 2 cases are frequency modulations. You see 2 values of theta. You see that frequency changes as well as amplitude. And here you have the amplitude modulation where you see the frequency is pretty much the same, but the amplitude is changed. Or notice that the axes here are different. So wrapping up this first part of the talk, I want to conclude something about this X-ray paradigm. And I can say that exert corresponds just to an open loop evolution. So there's really not much to draw as a conclusion from the exert for this example. The detect is really the core of the design, which is parameter dependent and allows you to adjust the output. And the reset is really an orchestration of the input. So it's like a pattern generation for the input. So these are tools that we need to sort of adapt to the application, and they are specific to this circuit. How can we draw some general conclusion? For now, we don't know. So let's move to the next example, and hopefully we will see some similarities. So in the next example, I want to talk about tracking in the presence of impacts, okay? So the idea is that you have two masses, Z and X, and both of them are forced to live in a polyhedral set. So when they reach this boundary, which is a hyperplane, they will impact. And if you do reference tracking, so you try to track a Z from X, you could do feedback linearization and it will work well in the flow. The problem happens at impacts. Because impacts are not synchronized, a lot of mess happens. And it turns out resets can resolve very elegantly this issue using mirrors and not using smoke. Okay, so historically, impacts have been studied a lot. You know, I kind of remember going back, you know, almost 20 years, Bernard Brogliato bringing his own Newton cradle in Ph.D. summer schools and showing experiments, right, with this Newton cradle. And there's been a lot of work done on Lyapunov-based solutions. What I'm presenting here is very connected to the reference spreading technique used by Alessandro Saccon and Nathan van de Voo and people in Eindhoven, for those of you who know that stuff. And it's work that I did with my former student Fulvio Forni and Andy Thiel about maybe 15 years ago. Okay, so let me tell you what the context is. So you have these two masses, right, Z and X, and both of them are characterized by a position and a speed. And these are defined in an n-dimensional space. The space where the area where they evolve, this set C, corresponds like to the inner region of some polytopic boundaries. And each boundary is defined like here by a vector f, whose norm is the distance to the origin. So the origin is also in the interior of this region, and the direction is orthogonal to the boundary. So there's a very nice way to write this down mathematically, which is just asking that this inner product is less than or equal to 1. Okay, so what is the detect? It's intrinsic to the plant. It's the case where any of the two masses, so let's call it S as a generic symbol, reaches the boundary, so this constraint is saturated, and the velocity is piercing the boundary, which we can express again elegantly like this. So what happens at the impacts is also something quite interesting. The speed is reflected in the orthogonal direction. So to describe it, we use reflection matrices, okay? So while doing this work, I learned about reflection matrices, so that's something I want to share with you. We are very much used to projection matrices in control field, which correspond to this matrix with a 1 here. So projection matrices have eigenvalues that are at 1 or at 0, right? And 0 are the projected direction of the operator. Now, reflections have eigenvalues at 1 and -1, and -1 corresponds to the reflected direction. So there's this fairly elegant representation of them, and you see we apply them to the speed. But the nice thing that we draw also by looking at the situation is that at impacts, we can apply the same reflection also to the position, because the position is at the boundary. And so reflecting the position generates the same position. So let me define this mirror operator here as something which is a reflection of both the speed and the position. So if we apply it to a mass which is away from the boundary, we will actually generate a reflected mass with respect to this wall, with respect to this hyperplane, as if it was reflected by a mirror, right, intuitively speaking. So we're going to use this later to fix the issues with convergence and stability of this system. But before doing that, let me talk about the exert. So what's the exert here? Well, we're going to let the exert be fairly generic. Again, Z has positions and speeds, and imagine its equations being just a standard, position-velocity relation, and then some generic acceleration that we know this alpha could represent maybe this spring in a two-dimensional space, or maybe the gravity in a bouncing ball, which is one-dimensional, or you could be creative and even pick time-varying versions of this. Now, as long as you measure it, what you can do is you track it with x, and for simplicity, let's take x to be a double integrator. If it is not, you can still cancel whatever nonlinear terms you know. But the natural choice is to just cancel alpha and then feedback the error, x minus z, through a gain k. And this makes the dynamics of the error linear. So all you need to do is to pick k such that a plus bk is Hurwitz, and you will get a very nice quadratic Lyapunov function, LTI flow, and just please keep in mind this notation for the transpose of the error through positive definite matrix P. Now, of course, everything works well without impacts, but with impacts, this is what happens. And again, the reason is that the control law gets confused by the fact that the impacts are not simultaneous. And this Lyapunov function, in fact, increases at impacts. Okay, so how do we solve this problem? We add again logic state Q, and let's look initially at one boundary, okay? So then Q is just either 0 or 1. And then we mirror the target through this M. So when we put 0, it's just Z. And when we put 1, we mirror it in this way. And then we just feed back the error, which is sort of hybridly reflected, so depending on Q. And so we design the feedback like this. We also need to reflect the alpha. It's pretty intuitive. And then how do we do the reset of Q? Every time there's an impact, we just toggle, okay? So with this trick, toggling, well, you get global exponential stability again. And the reason why is that by doing this, you're undoing the impacts in the aerodynamics. You see it here in this bouncing ball simulation, but you also see it here with the 5 boundaries where if you unfold the trajectories with respect to this boundary, you clearly see the exponential convergence. So this works well with one boundary, with global results, and for any k, linearly stabilizing. So that's very advantageous because it means that you can take very low gain feedback, deal with saturations and all that stuff. You don't need to compensate for a growth because, in fact, this type of solution is such that this Lyapunov function remains constant across any impact. Okay, so you resolved this problem induced by the impacts using these mirrors. Now, you can do much more. Like if you have specific shapes of these polyhedral regions, as long as you define sufficiently many reflected targets and 4 specific shapes, you can still get global results. And the key here is that you don't just toggle Q. And this is, again, the case where this reset is an orchestration among different targets, right? So we pick the best target as dictated by the Lyapunov function, and then we know that we get good behavior, okay? This is, for the specific example, a selection of the exert and the reset. Now, if you want to go beyond the global and, like even get away from polyhedral and just, define very, very general regions where the motion is constrained, then there's maybe infinitely many possible reflections that you can pick from. You still have an idea about how to do the exert, which is the same, and the reset, which is now a bit different. It's based on an argmin because locally this one will work. Of course, only locally, okay? Okay, so I hope that this clarifies another context where these 3 ingredients are, well, exert is fairly more general than before. Now, it can implement any feedback k as long as it is linearly stabilizing. And then detect is enslaved by the plant dynamics, so you have no control over it. But the complication, the true difficulty is in the reset, where you have to implement this specific orchestration, okay? Okay, so let me keep going, and let me talk about satellite rendezvous with chemical propulsion. Okay, so imagine here you have a target, and you need to reach it with a chaser satellite, and this chaser actually has chemical propulsion in the thruster. So what that means is that the thrusters are very powerful, and you turn them on for a very short time, over which you essentially experience a discontinuity in the speed while the position remains constant. And this type of problem has been often solved through optimal control in open loop, but recently aerospace engineering people are seeking for state feedback solutions that enjoy better robustness properties. And the dynamics of this system has been studied since the 60s. And there are several works that have been done also looking at closed-loop solutions. The work I'm presenting here, we did it with former student Mirko Brentari and former student Sofia Urbina and my colleagues Denis and Christophe from the LAAS-CNRS. I'm going to try to give you some context for this application. I'm not going to get to the end of what we did, but I'm going to explain the LTI idea behind it, and then it actually opens up a bunch of possible, say, continuation. And hopefully it will have some interesting tricks in it. So when you look at the relative position between the chaser and the target, what you typically do is to attach a reference frame to the target, and this is the so-called local vertical, local horizontal reference frame. So the position of the chaser as seen by the target is given by these three positions and these three velocities. Okay, so these are the states of the relative dynamics, which in this case is linearized. So the relative dynamics is nonlinear, but this is its linearization. It comes, already from the 60s, this type of thing. Now, what is interesting about this linearization is that it depends on this angle nu. Okay, nu is the true anomaly. And we know from Keplerian laws that it's normal, right? Orbital dynamics, they depend on angles better than on time, right? So this is like an LPV system. The matrix A is 2 pi periodic. You see this cosine. E is the eccentricity. So in fact, this simplifies a lot for circular orbits. And then with this A matrix, we have the input F acting through a trivial matrix B because it acts only on the speed, right? So you can see that the model, well, okay, so what you do, you take the integral of F over a very short interval of time, and what you get is an input U, which is impulsive, right? So you get a hybrid model of this form. You get free motion, and it's described by this LTV matrix A, and then you have impulsive thrust, where you change the speed, okay? So now the trick is to change the independent variable, and this was done already in the past, and it's done a lot in control, as many of you know. So what you do, instead of writing this as a function, instead of writing the evolution as a function of time, you write the evolution as a function of the angle, of nu, okay? So that becomes your independent variable, and then you get another differential equation where the domain of the solution is the angle. And in fact, you can add the angle as a state and reset it to 0 once it reaches 2 pi because of periodicity. So this angle will then evolve in a bounded set, which is convenient from the Lyapunov point of view. But generally speaking, this trick of reparametrizing time is very much used. They use it in legged robots, where they use the angle between the legs to do that. Or they use it in rotating machines, where instead of using time, they use the angle of the rotating machine. I'm not happy with this. I want to go beyond, because I told you this talk is about LTI flow. And so what we're going to do is we're going to take those previous equations and put them up here, and I want to apply the so-called Floquet-Lyapunov theory, which is something that allows you to transform LTV periodic motion into LTI motion. And in fact, with some work, Floquet-Lyapunov theory is not fully constructed, but with some work you can determine this change of coordinate R, which depends on nu, such that when you look at the dynamics in C coordinates, then you get a matrix A0 which is almost 0. So that means constant evolution, except for the last state. There's this little one that denotes a double integrator intrinsic to the fact that if, say, the chaser is in front of me and it's in a slightly different orbit and it's going faster than me, it will just get away, right? But the other states remain constant if this last state is 0. What's the price to pay for this simplification is that all the complicated stuff moved to B. So now we have a B, which is periodic, and which depends on nu, in a known way. In fact, we see also that the second input acts only on these variables, the out-of-plane motion, and the first and the third input act in the in-plane motion, the plane being the ecliptic plane of the orbit. But I think we want to now exploit this fact that this evolution is constant. And maybe I should also mention that it's a bit counterintuitive that for satellites whose relative evolution is always oscillatory, right? Why do we get constant behavior? And that's something I want to share with you, like another thing that struck me when I thought about it in this way, is that if you take an oscillating system, a linear LTI system, you can move its eigenvalues through a proper change of coordinates. We're always taught, you can't move the eigenvalues. No, you can. It's just, it has to be time varying. In fact, if you take a change of coordinate, which is a rotation, this system is transformed in this one. And that's what's happening here. So people working in control of electrical motors know this very well. Park transformation is exactly this. But we never think about it in terms of eigenvalues. And in this case, it's very helpful because this psi state remains constant. So we can plan when to apply the impulsive thrust with a bit more elegance. And elegance brings insight. Okay, anyway, let's keep going. So once we know psi, we can specify any reference relative motion, so these are some examples, by a selection of 5 parameters. Now, these parameters have geometrical interpretations that are understood, and then, once we know psi ref, we can define the error, and we can drive the error to 0 through this hybrid feedback, right, which acts at impulsive thrusts. So how do we do that? We're already in a very convenient situation. But one way to do it is, once again, to insist on timers. One thing I wanted to share with you is that you can put timers in your controller. So we have the green timer, which is the true anomaly, that we reset to 0 when it reaches 2 pi. Here it is, right? So we reset nu to 0 when it reaches 2 pi. And then we add a new timer, tau, an actuation timer. And every time we fire the thrusters, we initialize it to some value gamma tau, which is our detect feedback, right? And, this is sort of like the self-triggered scheme presented yesterday by Frank, right? It's one possibility. But what's interesting is now, if you look at the design, the detect is here, the reset is here. So you choose when and how to apply these thrusters. And it turns out it's a fairly simple task after you've transformed these things in this way. Why? Because, first of all, if you take the last state to 0, then the flow will be constant. And so you can wait as long as you want, epsilon will stay constant, waiting for you to move it wherever you want. So you can wait until the input matrix B0 is ideally placed. You can actually minimize, say, the consumption to take that state to a convenient place, right? And so there's a lot you can do. You can also keep the 6th state non-zero. It doesn't matter. The evolution. It's just an exponential. It's a very simple one, actually, okay? So I don't want to go beyond this for this example, but I hope I convinced you that transforming everything into LTI flow simplified the problem, and now we need to design, detect, and reset. So wrapping up, exert for this system becomes super simple, right? And detect and reset are really a way to characterize relatively simple non-periodic sample data feedback problem, okay? Okay, so I'm going to then get to the last example that I wanted to discuss today, and it's about dealing with friction in PID feedbacks in motion systems. Okay, so the rough idea is this one. So if you get a motion system, industries very much like to use PID feedback to stabilize them. And this is something that people in Eindhoven, they know very well, because they have lots of collaboration with local industries doing semiconductor manufacturing, and they have all of these nanometric positioning systems that they need to control. But at those levels, Coulomb friction, that I'm going to discuss in a sec, is really important. And it turns out when you implement PID with Coulomb friction, I will show you, you get asymptotic stability. It stays. But you lose local exponential stability, which is really bad. And you get these long and slow transients. So what you can do with resets, that I'm going to show you now, is that you recover the exponential convergence. Okay? Now, just to say a few historical words, you probably know that friction has gained so much attention, right? I mean, we can think about the 90s, the Lugre model, I see Carlos down there, and the Leuven model, and a lot of works have done in terms of modeling it. The model that I'm discussing here is the model based on differential inclusions, and I'm going to try to explain why. And then the work that I'm presenting is also together with my former PhD student, Andrea Bisoffi, and with former PhD student, Ruud Behrens from the Technical University of Eindhoven. So we'll spend a little bit of time on this dense slide. Sorry for too much material, but I think it's also good to have it under your eyes while we're explaining the context. So we have a mass, and the position is S, okay? So if we apply PID feedback, we have proportional, integral, right? So the integral of S is going to be this EI, and derivative action, okay? So it's fairly simple, PID action, okay? So what's the friction? The friction looks like this. So you have a viscous component, which is this one here, and then you have this discontinuity at 0. And that's the nasty guy. That's the Coulomb effect. How does it work? Well, if the velocity is 0 and the applied input is small enough, then the friction is exactly the same, so that their difference in the dynamic equation is 0 and the speed stays at 0. We experience that, right, on a table which has a lot of friction. Otherwise, if you apply enough input, then friction will always oppose to the movement. It will always be a braking force. Now, the problem is that this function is really ugly, and it's got what is called the causality reversal, where, you know, the friction depends on the force, or it doesn't depend on the force. And so there's a very elegant way of representing this with mathematics, I hope I will convince you, through a differential inclusion. So rather than writing it like this, let's put down all the forces that are applied, so U and then the viscous force, and then whatever remains is just a bounded term, which is a sine function times this unknown quantity F bar C. So away from V equal to 0, this is a single valued function, so it's simple and it corresponds to this. At 0, we're adding all this stripe, vertical stripe, among the possible selections that friction can make. And in fact, it looks like adding a lot of stuff, but the truth is that that equation, the same as this equation, has a unique solution from any initial condition evolving forever. And that solution is indeed what you experience when you experiment this type of thing. And so I like very much this because the right-hand side is better behaved. And so if I convinced you that it's elegant enough, then I would like to reshuffle the symbols, normalize all these constants by dividing them by m, incorporating in this velocity gain both the derivative action and the viscous friction, and then writing down a set of equations that depends on further transform the generalized position sigma. Sigma is really just the position scaled. And then a generalized controller state, which is essentially the PI action of the controller. Why do I do that? Because the equations are beautiful. And beautiful equations lead to significant results, in my opinion. So what are the equations? Like if you look at the derivative, again, you have position, controller state, and speed. You have this nice linear behavior in observable canonical form, so that Ki, Kp, and Kv are the coefficients of the characteristic polynomial, minus this bounded term, which is due to friction. So when friction disappears, this goes away, you get this linear dynamics. Now what I'm going to assume for the rest of this talk is that A is Hurwitz. So the PID controller must be designed in such a way that the linear motion is exponentially stable. This is a very mild assumption. It would be reckless to do otherwise. You would get very ugly closed-loop behavior, and so no industry would want to do that. But just to clarify, there's no other assumption that we're going to impose, and I want you to remember that this is the Spades equation. It's a bad equation. It's elegant, but it's bad because it doesn't behave well. Let me show you why. So this is an experiment on the positioning system that they had in Eindhoven. And you can see this is sigma, the position. This is phi, essentially, the control force. And it keeps visiting areas where the position stays essentially constant. The speed is 0. Those are called the stick regions. And the convergence is slower and slower. I also want to show you that experimentally, this model is fairly accurate, okay? And then the other thing I want to tell you is that this lack of exponential convergence, you can prove it through the Spades model. You can pick initial conditions arbitrarily close to the sigma equal to 0, v equal to 0 points, for which the stick time is arbitrarily long, okay? Despite these guys, the sigma not being 0. Okay, so with this in place, let's see what we can do. Now, first of all, let us analyze the dynamics. And so let's look at the Spades equation more closely. Let's look at that experiment or a simulation of it in the three-dimensional space phi sigma v. And you see that what's happening is that solutions are sliding along this red set. Now, the red set is the set of all the equilibria. In fact, if you look at these equations, the equilibrias are v equals 0, sigma equals 0, but phi can be anything smaller than fc. And so what is the best hope you have is to stabilize this set of equilibria, which is this segment in the state space, okay? Now, the truth is you can prove that that set of equilibria is globally asymptotically stable for any selection of the gains. And so this gives you a lot of degrees of freedom in picking, your PID gains. But the problem is that it's not locally exponentially stable, and that's the issue that we saw before. Now, before going on, let me tell you that the Lyapunov function establishing this result is fairly insightful, and it's discontinuous, so you have to handle it with care when proving stability and convergence. But let me also share with you that, you see, this behavior out here and out here is actually LTI if you look at it in the right coordinates. And that's how we came up with this Lyapunov function. So LTI flow was fundamental also here, okay? But let me show you how we exploit further this Lyapunov function, which is still down here. So let's look again on these trajectories and their behavior here. What are these long stick phases corresponding to? Well, they correspond to long times spent by the solution in this stripe that I called the stick region. It's a horizontal stripe where v is 0, phi is smaller than fc, and sigma is any value. So it's like a long stripe. And what happens with this is that solutions enter on one side and take a longer and longer time to exit on the opposite side. So what's the idea? Let's reverse the sign of phi. So we jump across this stripe, okay? So let's do the reset in this way. Reset phi to minus phi at this point. How do we detect that point? First thing, let's look at the Lyapunov function. When is it that it doesn't increase if we reset phi? Phi v less than or equal to 0. This comes from the second term. So that's the first thing we're going to add to our detect law, okay? So our detect law is having this term here, which is Lyapunov induced. And then we include another term because we roughly know what trajectories are doing, and it makes a lot of sense to reset after an overshoot. Okay, so this is more coming from an understanding of the physics of the problem. And so we add also this condition, and then, you know, we add also this condition on two resets not being too close one another, but it's not a very important condition. It will be only active when we're extremely close to the attractor, because otherwise things are done right here. You know, when this is non-zero, then this sign reverses, and so if you reset phi, you're already in good shape. The other thing I want to do is, instead of just changing the sign of phi, I want to also shrink it a bit through this alpha. Alpha helps me obtain a bit more robustness in case friction is not symmetric. But then I'm going to just concentrate on alpha equals to 1, because that's the most interesting part. Okay, so that's what happens, and it works really nicely. So you see that you jump to the other side of the stick region, you look at phi, and you realize that it's really jumping up and down. In fact, you can show that its norm converges to the unknown value of Fc, right? So it's a sort of a weird way of estimating Fc. And you can prove global exponential stability, global asymptotic stability with this trick. You cannot prove global exponential stability even though you see it in the Lyapunov function behavior. It decreases exponentially. But why can you not prove it? Because those bad initial conditions in the stripe, they still exist. Except solutions starting outside, they never enter there. So how do we characterize that in terms of you know, some rigorous result? Solutions subject to certain initial conditions. It's weird, you know, like I don't know exactly how to do that. Anyway, so this works, and what can we say about exponential convergence? I don't really know. But what I can tell you is that you can look at certain output variables, which are weird. It's exactly because phi never crosses 0 that you can sort of subtract this term from phi. And then what you're doing is that you are collapsing the segment A into the origin. And then you look at these trajectories, they really look linear. They're not linear. So there's a weird homogeneous dynamics that governs those states, depending on Q, which is sort of the stick slip condition, and on the sign of phi, which keeps toggling. But still, I think it's interesting to look at it this way. And again, thinking that we always seek for LTI shapes, you know, when we look at trajectories. But maybe Miroslav wouldn't agree, because he masters nonlinear better than I do. Anyway, so this is an experiment showing that it works very well. So the case alpha equal to 1 is the most interesting one. The gray areas are areas where the resets are disabled because you reach the precision of 10 nanometers that you wanted to get. And that's a further illustration. So back to X-ray, you know, exert is again arbitrarily tuned PID. And then detect and reset are, you know, sort of Lyapunov helped us in defining them, and they depend a lot on the application. And this brings me to the end of my talk, and I wanted to draw some conclusions. So how did we exploit LTI flow? It was always because we wanted to get some Lyapunov proofs. Maybe the only exception is this one here, because I didn't get the time to show you what you can do in terms of Lyapunov, but I promise you there's a lot of Lyapunov results that you can obtain for this case, exploiting this behavior of the quasi-constant state. Now, in terms of exert, detect, and reset, we sort of see a separation, as if exert is either nothing to do because it's just the open loop behavior, or arbitrary, full degree of freedom. You can design it in any way you want, and then the detect and reset will take care of the rest. So there seems to be a hierarchical design paradigm that could come out of this, where this is really like the detect, the reset is like an augmentation. But then maybe it's just because I didn't look at enough applications. I didn't tell you about walking robots, which is another example, but we get the same architecture over there as well. And then in terms of detect and reset, we have so much variety. Some cases are, detect is induced by the plant. We can't do much about it. Some cases are the ones where the detect is the fundamental input. That's my question mark for today. I really have no idea. But I wanted to share with you the fact that I didn't talk at all about all the tricks in the Lyapunov constructions, the proofs. I felt this was really not appropriate for a large audience talk, but at least one slide on what's under the hood, which is really complicated. And so the first thing I want to say is that hopefully you understood that we have powerful, novel control design tricks that we can apply. And Uncle Ben said that, we have to take great responsibility with great power, so we have to do that. It wasn't Uncle Ben, though, but anyway. And then I want to tell you also some lessons I learned when looking at Lyapunov constructions. When you do this interplay of exert and reset, a lot of complicated things come up. Optimization techniques become important. Often you want to minimize this Lyapunov function, and you get nice decreased properties. And then often, because you add resets, some systems that had some nice cascaded form, the cascade is broken. So you sort of even reverse the cascade. So there's a hierarchical structure, and when you add resets, resets reverse the cascade. And so we need tools to address those things. Of course, the basic thing is to compensate terms in Lyapunov functions, but can we do something more substantial? And so that's all work to be done. And in fact, there's a lot that we can draw from hybrid systems theory, hybrid dynamical systems theory. I want to mention that the examples I talked about today can be partitioned into groups. The case where the reference is known and the case where the reference is emergent, when you don't know it. Now, the first case is the one less explored. I think that hybrid Poincaré theory is very powerful, but I think we need set-valued maps. And I think the recent book of Raphael Goebel is a very nice place to go and look for building this theory. I think we could use contraction theory for hybrid dynamical systems, which is highly underdeveloped for addressing this type of problems, or even look into P-dominant formulations, which exist for continuous time. Now, when you can measure the tracking error because you know the reference, you can do much more because a lot of results exist. And I want to share with you that you never, or almost never, have a strict Lyapunov function. So you always get decrease along flows, but then non-increase at jumps. And so you always need LaSalle, and there are tools out there, even for LaSalle results that are non-smooth, which you often need because when you have these timers, sometimes you add in the Lyapunov function the maximum of the timer, between the timer and a certain maximum value, which is non-smooth, and so you need those tools, but they're already there. I want to publicize Matrosov formulations. I really love this thing, for those of you who don't know it. There's this very nice and descriptive paper from 2009, and then in 2017, Dragan and Andy published a very effective tool for Matrosov constructions for switching systems. I mean, tools are really out there. But generally speaking, I think I also want to share with you the fact that I've been understanding how you can exploit this interplay and flow and jump to go beyond flows that give you decrease in the LTI sense. So you can easily get very aggressive control systems where the flow is exponentially diverging, and that promises a very aggressive control action, and then the resets take care of the rest. And I guess with this I am done, and I thank you very much for your attention.
Okay, thank you, Luca, for the very interesting talk, and we are looking forward to more results and applications on this theme. Thank you so much.